Assalamualaikum and hi everyone, welcome back. This is pre-recorded video 12 for chemical bonding. In the previous video, we have discussed the theories of chemical bonding, specifically about valence bond theory. In this video, we are going to learn the second theories in chemical bonding, which is VSEPR. So, why do we learn this theory? It is because this theory can predict the molecular geometry or molecular shape of a molecule. By definition, the valence shell electron pair repulsion or VSEPR theory states that the electron groups around the central atom will be most stable when they are as far apart as possible. And this actually leads to molecules to have a specific shapes or molecular geometry. First, we need to understand the terms in VSEPR. We begin with the electron group geometry. This is the first term, electron group geometry, which is determined by the locations of regions of high electron density around the central atoms. You cannot see that, but you can, the electrons region or the density of the electrons. Okay, the second term is molecular geometry, which is the shape of molecule is determined by the arrangements of atoms around the central atom. Okay, we have central atoms, we have terminal atoms. Central atom basically in the middle of a molecule. The electron pairs are not used in the molecular geometry determinations, just the position of the atoms in the molecule are used. Okay, so you know two terms already. First is electron group geometry. The second one is molecular geometry. It's different. Okay, so let's focus first on the electron group geometry. It's actually a collection of valence electrons localized, centered in a region around a central atoms that repels other groups of valence electrons. That's the definitions of electron group. And ideal molecular geometry is based on this idea that pairs of valence electron in bonded atoms repel one another. Why? Because it's electron and electrons, right? The same charge, so it repels one another. And the mutual repulsion among electron groups lead to an orientation of the group, and this is called electron group geometry. Electron group geometry. So in electron group geometry, we can expect that electrons on the central atoms to be arranged so they are as far apart as possible. There are a few categories of electron group geometry based on the numbers of electrons. For example, 2, the geometry is linear. 3, trigonal planar. 4, tetrahedral. 5, trigonal bipyramidal. And 6, octahedral. Okay, so this is the electron group geometry and also the molecular shapes. We are going to learn more later. To make it more clear, let's take a look at table 9.1 here. Some book calls electron group geometry as electron domain geometries. It is the same thing. For number of electron domains 2, the electron group geometry is linear. Okay, and the bond angles is 180 degrees. For 3 electrons, okay, the electron domain geometry, we call it as trigonal planar with bond angle of 120 degree. And for 4 electron domains, number of electrons domains 4, so we call it as tetrahedral. So the angle between the angle between the atoms is 109.5. For 5, number of electron domains. The electron domain geometry is trigonal bipyramidal. The predicted bond angle can have 90 and 120 degrees. And last but not least, for 6 electron domains, okay, the name of the geometry is octahedral. So the predicted bond angle is 90 degrees. You can see clearly in these slides. So you have to understand that and remember the angles responsible for each electron domain geometry or electron group geometry. This is what we have to know about, we ask EPR, the AXE. AXE, okay, which A is refers to the central atom. For H2O, the central atom is oxygen. X is the terminal atoms. Okay, for example, in H2O, terminal atoms are hydrogen. And the lone pairs is refers to E. So there are 2 lone pairs in H2O, AXE. Back to VSEPR table, let's have a look at the electron group 2. Okay, so remember electron group 2, 3, 4, 5, 6, right? So VSEPR notation is different for number of electron groups and also VSEPR notations. So we know that A is the central atom, X is the terminal atoms, and E is the lone pair. For this case, the number of electrons only 2. So number of lone pair, there is no lone pair electrons. The molecular geometry is XAX, which is linear. And then the bond angle is 180 because it's linear. Okay, so maybe you have to understand that how this 180 is measured. So it's the angle, this is the angle, 180. For example, this is for beryllium dichloride. The optimal repulsion arrangement is opposite end of line. And then geometry is unaffected by lone pairs of electron because there is no lone pairs in this case. It's only A, which is terminal A is the central atom, in this case beryllium. X is the chlorine, okay, X2. There is no lone pair. Now this is a trigonal planar. Trigonal planar is a molecular geometry with 1 atom at the center and 3 atoms at the corners of an equilateral triangle, also known as peripheral atoms, all in one plane, shown by the red triangle in the slides. Okay, an ideal trigonal planar has 3 identical ligands and all bonds angle are 120 degree. Okay, you can see here the first one, right? The electron group geometry is trigonal planar. The VSEPR notation is AX3, meaning that there is 1 central atom A and 3 terminal atoms. In this case, boron is the A, which is the central atom. Fluorine, 3 fluorines, meaning that AX3. So AX3 is the electron group geometry is trigonal planar. The molecular geometry is trigonal planar too. The bond angle is 120. So you can see the molecular model as this. The optimal repulsion arrangements is the corners of triangle. Okay, note the planarity. So it's planar here. It's the same plane. Planarity is on the same plane. Okay, and then with a lone pair, the geometry is essentially the same because it still has a number of electron groups 3. Trigonal planar, the electron group geometry or domain geometry, trigonal planar. However, it has 1 lone pair. So the formula or the notation for VSEPR becomes AX2E, which is trigonal planar, but the name of molecular geometry is different. It's no more triangular planar, it's angular because it has lone pair here. For example, SO2. And then the degree of the bond angle is still 120. Okay, so this is a number of electrons group for 4, which is tetrahedral, which means that an object that has a central atom surrounded by 4 other atoms. The angle formed between bonded atoms are 109.5. This system adapts with SEPR notation of AX4. There is no lone pair for this case. Okay, so this is called tetrahedral. This is central atom and then 4 terminal atoms. For example, CH4 or methane. The optimal repulsion arrangement is the corners of a regular tetrahedron, 4 equal triangular faces. You have to remember this angle. Okay. However, there can be 1 or 2 lone pairs on the central atoms. For example, this one. Okay. Number of electron groups still 4. Tetrahedral is the EGG or electron group geometry or domain geometry. Lone pair 1. Okay, so notation is AX3E. So you can see here the lone pair. We cannot see lone pair, all right, because there is no atoms on the top here. So it's still tetrahedral EGG as EGG. However, in geometrical look, you can only see trigonal pyramidal, because this is trigonal here, and then it looks like a pyramid. Okay, so for example, ammonia, the molecular model is shown here. And there's another case of tetrahedral with 2 lone pairs, AX2E2, and then this is angular, called angular because you can see AX2 here. Okay, however, it actually has one more, which is E2, lone pair, 2 lone pairs. So the bond angle still 109.5, for example, OH2 or H2O. Okay, water. Next is trigonal bipyramidal. By definition, is molecular geometry, 1 atom at the center and 5 more atoms at the corners. Bipyramids means that the optimal repulsion arrangement is a triangle with a bisecting line through the triangle face. So this is a triangle, you can see here. Okay, so it's bi, so it pyramid up and pyramid down here. Okay, the bond angle can be 90, 120, and 180. So this is case for AX5. There is no lone pair. Okay, so another case when there are lone pair AX4E, so you can see actually seesaw. Okay, the molecule looks like a seesaw. Okay, so actually it has a lone pair here, you cannot see. So this is a seesaw. And then for 2 lone pairs AX3E2, it is actually T-shaped. Okay, can adapt 90 and 180 degrees. For example, a ClF3 here. And it can have 3 lone pairs AX2E3, and this is actually a linear molecule. So A180 is the bond angle, for example, xenon difluoride. And the last one is an octahedral, which means a shape of compounds with 6 atoms or group of atoms symmetrically arranged around a central atom, defining the vertices of an octahedron. This molecular geometry has 8 faces, hence the prefix octa. Okay, even though actually it has 6 atoms, it is named octa. Why? Because it has 6 faces. So this is 1 face, 2 face, okay, at the back, the 3, and then 4, okay, and then the other 4 is at the bottom. Okay, so it has 4 faces. So this is in the case of AX6. Bond angles is 90 and 180. For example, sulfur hexafluoride. The optimal repulsion arrangement is at the face centers of a cube. Okay, and 1 or 2 lone pair geometries are most common. For example, here you can see octahedral one with 1 lone pair AX5E. Actually, it can become square pyramidal. Square, why square? Because this is square here, and then pyramid. Okay, for the bond angle is 90 degrees. And the example is BRF5. And the last one is a number of lone pairs 2, AX4E2. This is called square planar. Okay, so you have to differentiate between square pyramidal, square planar. Square planar has two lone pairs. Okay, you can see only these four, XA, X4. Okay, for example, xenon tetrafluoride. Okay, the ideal bond angles is 90 degrees. That's all the end for VS EPR part 1. Thank you and see you in the next video.